I'd like to thank the organizing committee, both here in the United States, for inviting me on this opportunity. I've learned a lot and met a lot of wonderful people and have generated collaborations from the preemptive, and I'm looking forward to the same experience as we go forward here. So my talk today is going to focus a little bit on something I've been doing recently, which is something that I haven't been doing for very long. And so it's something that's a little new for me and I think a little different from what we're doing. So I'm going to talk a little bit about Hurricane Michael itself, what happened, somewhat recent event, and then I'll talk about a couple different trips I took back down to the region and some of the different performance things that we saw specifically related to low-rise buildings and what happened to them. And then I'll talk in a little bit more specific nature about a follow-on study related to the National Science Foundation, a RAPID project we got, where we looked at a specific class of buildings based on a number of different failures, structural failures that we saw during the initial reconnaissance efforts. Just as a little bit of a background for what I do in general, I like to be in the lab, but that costs a lot of money. And so I don't get to do it as much as I want. Breaking big things is one of the fun things I get to do on my job. I really also do a lot related to nonlinear analysis of components and systems, and most of my career has been related to earthquake-related research, passive energy dissipation, ductility, different types of fuses in structural systems. I'm also, having been a practicing engineer for several years, the structural design aspect of this is also important to me. I've been in part of development of innovative structural systems and devices for extreme events, again, primarily seismic related, but also with consideration for other potential hazards. I've done a lot of work related to bridges, and then I've been involved in several different post-event reconnaissance missions, Hurricane Michael being the most recent, and I've also worked with some of my geotechnical colleagues quite a bit on soil structure interaction, which I find quite intriguing. All right, so let's get in and talk about Hurricane Michael itself. It made landfall as a Category 4 hurricane, which is pretty significant, on October 10th, 2018, so just about 4 or 5 months ago. The eye wall track, and we'll show a map. The eye wall track hit just south of Panama City, Florida, when it made windfall or landfall. Maximum sustained winds of in excess of 150 miles per hour. So it was a very significant storm, fourth largest storm to make landfall in the United States in recorded history, and the largest to make landfall in the panhandle of Florida. Our best estimates indicate that within several regions, even far from the coast, the design wind speed the wind speed exceeded the design of the code, and the damage extended significantly inland. So it wasn't just at the coast. We were doing damage assessments well into the coast, even north of Interstate 10, if you're familiar with the geography there. And then this one was a big one, and I'll show this a little bit, but I don't talk about it too much. But the storm surge in the area of Tyndall Air Force Base and east towards Mexico Beach was 8 to 12 feet, and I've even heard more studies more recently, I haven't seen this published yet, but in excess of 13 and 14 feet in certain areas. So, you know, we're talking about a pretty significant wall of water. So this is the, does this pointer work? No. This is the map here. These contour lines are wind velocity contour lines. So you can see here in this little area is where we got the 150 to 155 miles an hour. That 140 mile an hour contour line actually extends pretty far inland, and then but you can see that it dissipates pretty quickly down. We were staying over here after the damage. We were over in this area, and you could hardly tell that there had been a hurricane come through. And so this area here in the 110 to 110 contour over to the other one was where we saw a good bit of the damage. And even within that region, there was some pretty significant variation. This is kind of a more local view of some of the areas where we did a lot of our reconnaissance. You'll see here the most populated area is Panama City up here and Panama City Beach. And in general, that was in a 120 to 130 mile per hour zone. This area down here, this is Tyndall Air Force Base. If you saw any of the pictures, and I have a few of those of some of the big hangar structures that experienced significant damage, that's where it was. And the big storm surge area was in this region right here, the eastern edge of Panama City down through Mexico Beach. This shows this is from what we call a website called Fulcrum, and this is a website that we use to categorize and assess structures in a very systematic way. And this is a neighborhood that's called Cedar Crossing. It is within the Panama City region. And each of these dots represent one of a number of buildings that we did a door-to-door assessment. In other words, we would go up and take pictures. We try and stay off people's property unless they're there and they let us in, but we take pictures and we assign an assessment value from destroyed up to undamaged, blue, green, yellow, orange, and red. And you'll note here that we've got all these structures along this roadway. We don't get every one. We try and do about 1 in every 3 structures to be systematic and unbiased. But you'll see that pretty much there was one structure that was considered undamaged out of these. And this was a somewhat recent neighborhood, but probably most of it built in the early to late 90s and early 2000s. Of the 40 buildings we assessed, there was 1 undamaged, 27 had minor damage, 10 had moderate damage, and 2 had severe. And when you look in a little bit more detail, the pre-2007 homes experienced more prominent roof cover and cladding damage. And some of that is just due to the fact that the roofs are older, right? Asphalt shingle roofs typically have a lifespan of in the neighborhood of 25 years if they're put on correctly. But a shingle roof that's 10 years old is not going to do as well as a shingle roof that's 5 years old. And so that aging perspective does come into play. But the other aspect is that the code had changed as we went through time, ASCE 98 and then 2002. The code-based wind values changed as well. One of the really cool things that we can do now in order to help us with these assessments is we do drone flyovers. And so we will set up a drone. I'm not sure if we can see. In this case, we had to set up 3 or 4 times to capture this, but then from the drone imagery, the drone flies overhead and takes pictures in an overlapping pattern. We can then kind of see and identify the damage on a single photograph or a single, this is called the structure from motion imagery, where they take this and this is actually a 3D point cloud type representation of what happened here. So the processing of this is pretty significant, but we're able to go in about an hour or 2, we can cover this whole area with drone flights and then process the data and have this for further review. So if you look at the damage, nearly complete shingle loss in a lot of cases. You see a lot of garage doors that get blown in or sucked out depending on which direction the wind goes. And a lot of fences are down as well as other damage. You can still see in a lot of cases the owners haven't even come back to remove the plywood that they have to, by law, they have to have in this area to cover the windows to prevent damage from flying debris. This is another neighborhood, and the reason I put this one in here is this one was in Mexico Beach, and it happened to be within about 200 meters from one of the towers that the University of Florida put up to measure wind speed. But this neighborhood was a much younger neighborhood in that all the houses had been built within about the past 5 years. And so you'll note here, and we'll have all the numbers, but there are a number of houses here now that are undamaged, and they're really almost all the rest of the houses are minor damage. And it's because of the more current code version as well as the construction methodology that they used then. So total of 15 structures were assessed. This was a smaller neighborhood. We had 3 that were undamaged and 12 that were minor damage. And so a much better overall performance of these buildings, and a lot of that is because of the construction age. And so even if you're keeping up with normal codes, once a building is built beyond a certain limitation, something needs to be done, all right? Earthquake, hurricane, whatever the case may be, as structures age, their properties generally degrade, and it's something we have to consider. Here's some kind of representative photos of what kind of damage you would see here. You have here, we've got a little trim panel on the edge. Here you have a little bit of asphalt shingle damage as well as some trim. And then this happened in a number of different cases with these houses, but because of how well and how newly they were constructed I don't know if you can see all this white stuff. Anyone have any idea what that is, this white stuff down here? What's that? It is not sand. It's roof insulation. So basically you lost this underneath here, and because of the suction pressures that are generated during an earthquake or during a hurricane, it sucked it all out. And so all of the insulation, the blown-in insulation, had been sucked out of the inside of the roof, and it was all over the place. But the thing is most of these houses didn't even have any water ingress problems, which is a very common problem once your building envelope, all right, is penetrated in some way. Often you'll get some significant damage from water blowing inside and causing damage. But in fact, this house, the person indicated to me that they were in the house during the hurricane, which they also indicated they would never do again. And were just because the way they described it was a freight train going next to their house for 4 hours long. I mean, that's what she described it as. But no interior damage, nothing. And that was, these are houses that were built much more recently to the current code, and it clearly shows that the things we're doing are having an impact. Mexico Beach. Now these pictures here are a very broad overview of what happened, and a lot of you may have seen different images related to Mexico Beach because it was almost complete and utter devastation. When we talk about earthquakes, we always talk, in more recent years, we talk about tsunamis as well, especially with the Indian Ocean tsunami and the one in Japan. Well, the storm surge aspect of hurricanes is similar because we can design a structure for an earthquake or for wind loads, and the expectation can be pretty good. But when you start talking about storm surge or hydrodynamic forces from flow, it gets pretty extreme. So this is the lone standing house here in this area, and all the rest of these piers represent locations where other houses were standing before the storm surge hit. All right, and part of it is that in earlier years, the storm surge estimates, the minimum height that they had to build on these stilts above ground, were raised over the course of years because of the additional studies and so this house just happened to be new enough that it was built once the storm surge height was raised enough that the stilts got it up. I don't know if you can see this. I'll take a picture. I have a better picture of this. This house was not there originally. It was somewhere over here. Okay. That's a close-up picture of that house. You can see the house is pretty much intact. It just got picked up off its foundation and floated to the other side of the road. All right, so they used to have beachfront property, and now they have, now they're attached to this hotel right here. In addition, in some areas, the storm surge did not actually get up and over the road, but the erosion that it caused due to coming up and hitting the road. I mean, this is a palm tree that's probably 30 or 40 feet tall, and this right here is about 5 or 6 feet of height between the height here and the height down at the bottom of that location. You can see that here, this is the center line of the road, and there's actually places on this road where the road doesn't even exist anymore because it wiped away the entire road. And you can see here, here's places where structures were that there no longer are because they were literally pushed off their foundations and moved. All right, so this is a video I took, and yes, I was driving while shooting this video, but it was a one-way road. So you can see here the debris piles and the extent of the damage that occurred in Mexico Beach due to this kind of scenario. So this is an area that there's been a lot of work going on, but in generally, as with tsunamis and storm surge, the only good way to build a structure to meet that is to get it up and above the level, or the other area that has been talked about is having blowout walls. In other words, once the surge hits, walls are designed that are there for a given wind pressure, but once a certain pressure hits, they literally blow out and pop off as designed, so that then the flow can be unobstructed and the structure above can remain. So because when you start talking about the magnitude of hydrodynamic forces and flow, it gets very, very significant. So while we were down there, we were doing a lot of driving around and taking pictures. And I've done research in the past on metal buildings, low-rise metal buildings in earthquakes based on some things I saw in New Zealand. And so I've always had, now that I understand them a little bit and I've done research on them, I'm always kind of on the lookout. And so I started noticing that a lot of these buildings had kind of a very similar thing going on, is that they were failing in a way you wouldn't necessarily expect. Well, you don't want them to fail. But I started just taking a lot of pictures, and we would see these pretty substantial buildings here that were having, this is the end wall of the building. This building is, this is a boat storage facility, all right? And it's probably 50 feet tall and several hundred feet long and wide. So this was a pretty significant building, and just one end of the building happened to be pushed in. You'd see a failure at the roof level here that would cause, it would generally be arrested at some level by the remainder of the structural system, but there was a localized end wall failure. And we started noticing that this was a pretty common thing. This is a high school building, and so this is the auditorium end of the building. This is a little bit different, but again, we have the end wall of the structure failing. We see a lot of the brick. This one's a little bit different, but a pretty significant structural failure, because a lot of failure in wind, cladding and components failure. We've got eaves, we've got other roofs that fall off, but for us, the things that really cause life safety issues are these actual structural failures. And this is a school building. This building is literally just 100 meters north of the other one that we just saw. And again, you'll see that this particular end wall had a pretty significant failure. You can see the purlins up there and the shape that they're in. This is a larger industrial metal building. This was a manufacturing facility that did steel fabrication, all right? This had been cleaned up. The end wall of the building was out here, all right? And it had blown in this way, and they had been cleaning it up so that they could get their stacked material in there out so that they could sell it and get it moving in other properties. Here's one that was a much more significant type failure. Again, this wall, the building is collapsing here, and everything is moving in that direction. Tyndall Air Force Base, I don't know how much you paid attention to it, but almost every building on Tyndall Air Force Base was damaged in one way or another, and some of them pretty significantly. So this building right here was an aircraft hangar building, all right? And Tyndall Air Force Base has the F-22s, all right? So when you think about things, for, saving a life is clearly an important thing, but these F-22 aircraft in generally cost in the neighborhood of in excess of $100 million each. I don't know the actual number, right? And so you've got a building that may cost, I don't know, $4 or $5 million to build, and it may cost a couple $1 million to re-roof it every 10 years. But if you're storing several $100 million in aircraft within a building, think about the potential issues. So this building right here, again, had an end wall failure. It's kind of hard to see from this picture, but the frame over here is literally bent inward, and the whole wall is pushed back into the building. This is a similar building right across the street from it. In this case, the cladding was pretty much torn off. If it wouldn't have been, there would have been a more significant failure. This roof frame beam was bent inward due to the positive wind pressure. This is a picture that it's probably, this is one I took, but this hangar building was where there could have been 20 or 30 aircraft, and the roof was entirely ripped off. And what it turned out was that this is the original roof, and instead of re-roofing it correctly, they just went and installed a new roof over the top, all right? And what that means is that's great, it keeps out water, but in a design wind event, you do not have the capacity you need because your roof is not directly connected to your structural components below it. It's connected to something else that's connected to the structural components. So this is a case where, this is a significant building that would have cost a decent amount to retrofit, but there were multiple aircraft in there, and clearly they haven't indicated whether or not they were damaged, but we know there were at least 22 F-22s here on this post during the earthquake, or the hurricane. We went back after a couple of weeks. We worked with the National Science Foundation because we identified this particular issue that we thought was pretty important related to these industrial buildings. And so we went back to do a more detailed review other than just take pictures and drive through. And we found these are three buildings that we were looking at that I'll show you next here. We've got a little bit more detail on them that are buildings that were damaged in a way that we feel is unacceptable. So if we look here, here's my 120 mile per hour wind speed estimate, here's 130. So all three of these buildings have roughly the same wind velocity that they experienced, all right? And so we're looking at these three buildings now in a little bit more detail. So the first one is what we call the Watson Marina building. So if we look at the map here, we had an expectation somewhere in the neighborhood, depending on how tight we get our going between the contour lines, we're around 123 miles an hour. Now, if I look at the ASCE 710 map through the ATC website, for a risk category 2 building, that would be 134 mile per hour design. For a risk category 3 building, that would be 144 mile per hour design. Now, this just stores boats, so it is not likely a risk category 3 building. So the design wind should have been 134 miles per hour. We have the drawings to verify that they use something in that neighborhood. And so it's a pretty substantial building, again, probably 50, 60 feet tall, about 100 feet wide and a couple hundred feet long, and this is what happened to it, all right? And when you look at the map, this is the wind direction where the positive pressure would have been the highest wind velocity on this face, all right? So when wind hits a building, you get positive pressure on the windward face, and almost every other surface develops a negative pressure, all right? And so this then, at some point, this kind of failed inward, all right? The damage, when you were in the other end of the building, you couldn't tell the building was damaged. The only damage was within these first two bays of framing. And if you look, and what I want to highlight is what you can see on these roof purlins. You can see evidence that these ones clearly are buckled and have had some pretty dramatic failure. But even back here, a few bays in, you can see where these Z purlins, which they're about 10 inches deep, and they're a light gauge metal, are buckling due to a compressive force. If you look closer, you can see it here. You've got it here, you've got it here. These are continuous over the rigid frames, all right? But you've got a lot of evidences of significant compressive forces that are causing buckling of that. So that's one building. This building, and this is one that is somewhat heartbreaking. This building is on the port facility for the Port of Panama City. They received a certificate of occupancy on October 1st, 2018. The hurricane hit on October 10th of 2018. All right, and you can see that there's damage here along the eaves. All right, you've got a rail station right here with a pretty significant cantilever overhang. But if we look at the other end of the building, that's what it looks like. All right, so you can see a lot of similarities in the way this looks. All right, Slightly different structural system. This is your typical metal building system, but it's a very large system. All right, so you can see these rigid modular frames with interior columns, but you can see the framing here, which is open web steel joists, are non-existent anymore. All right, and so we looked at this building, and we do have drawings again from this building. And if you look very closely, you can see that these open web joists are buckled in many different locations. It's hard to tell when you're doing this forensic analysis what happened first, what happened second. But when we look at the inside of the building, it's pretty clear that at some level, these things were experiencing some very significant compressive forces, were buckling and causing the loss of the diaphragm action at that level. The last of these buildings that I want to show is a third type, and this is a port of Panama City, so unfortunately the port got hit pretty hard. This is further inland, but this is a tilt-up wall building with interior steel columns and a typical steel roof framing system with joists and joist girders running in both directions. All right, here, this is an original part of the building. This was an add-on in 2013. So this building is not as new as the one we just saw, but still pretty new. And basically, we had a similar thing, but the difference is the precast panels at this end had all collapsed out, and a few on this side had collapsed out, and you can see the total loss of the floor system within. And here I want to point at this. So this is the first interior column, and there was a joist girder over here that was over here, and you can see the indentations here from the bottom flange of that, or the bottom chord of that joist girder hitting this tube steel column, indicating that the compressive force coming from the wall into the lateral system was a driving factor in the failure. Here is another one with a very similar but a little bit more extreme. It's nice that it has continued to rust, so we can see where the paint broke up due to the flexing of the system. And then this is one of the joists that would have come out onto the precast wall, and you can see along its length, this was a welded tie together that due to the compressive force it caused buckling along that length. And you can see it even better here in plan as you're looking up to see that the failure of this was not due to an excessive vertical load, but instead some sort of a buckling mechanism. So what happened? Well, we had a large sustained positive pressure, wind velocities in excess of 120 miles, less than the design wind, but still very high. It also generates an uplift on the roofing system, and often with these systems the roofs are so light that the uplift wind pressure will exceed the dead load and cause an upward movement, which is why winds or roofs get sucked off in hurricanes and planes fly. And the roof members, the roof framing members, whether they're purlins or steel joists, they have to take that reaction from the wall into the horizontal roof trusses. All right, and the question is whether or not they can. And what we believe, we're working on this now, is that the failure was initiated by buckling of those roof framing members, which removed the support of that end wall, causing them to fall inward. So pictures are generally better for this type of thing. So if this is my wind, and I've got a windward wall here, so I've got some wall system that's taking the load, and it's going to span up to down here. And I've also got at the same time a roof uplift, so I've got an upward flexure, and I've got a force coming in here. These are going to have to take axial forces in my diaphragm. If I look at that in plan, the way these diaphragms typically work is I have tension-only bracing. So very slender rod bracing, or maybe an angle, a 1 or a 2-inch angle. And then I've got the roof framing elements, right, that might be Z-purlins or open web steel joists. Well, what happens is these ones that I've got highlighted in red, you can't just have tension, right? You always have to have some tension and some compression. Well, these elements here are going to have to be the tension or compression struts in my tension-only system. And what we feel like is that these elements were subjected to compression forces that either they weren't designed for, or that the capacity was not there, we honestly don't know. So we're looking at this problem right now because we feel like this is an issue with the load path that relates to a pretty significant problem. You know, there are a number of these structures that did well, but the fact that this happened on these larger structures is indicative that it's something that occurs in every structure, but the problem only gets too big when you have a very large volume. So that's our working theory for the moment. And what we're doing is we've got this detailed investigation. We have plans for all 3 of these buildings. We have taken LiDAR data, so we're going to have point clouds. We've got structure for motion from UAVs where we were able to fly over these, so we're going to use all this information to develop an analytical model that we can then use, and hopefully if it comes out the way we expect it, at some point we can then look back to determine if there's some experimental testing necessary to determine how we can solve this problem, and that would be in a future project. So that's all I have. Something that's a little different from what I normally do. Sorry, I kept saying earthquakes. That's just, 10, 15, 20 years of earthquakes. You can't just turn it off into hurricane. But it's something that to me is it also has some aspects related to earthquakes because load path and understanding your load transfer in elements is of very critical importance in all that we do as structural engineers, independent of the hazard. So I don't know if we have time for questions or if it's time to go to lunch or what.